Today, did I already say this? Today is possibly the most important day of your life. Did I say it already? Okay. Today is the day you get to learn the fundamental theorem of calculus. Prepare your hearts and your minds. Yes, Vivek. Come again? I don't think you could, in your early days, I don't think you could have handled the truth. You know what I mean? You'll see. When we get there, you'll see that you need it all. You need to have been at this point in your life before you heard it. All right, before we even can set the stage really to even state what the fundamental theorem of calculus is, which is the exciting result of the day that will happen soon, but we need to talk about this function. It's called the accumulation function, and let's play around with it a little bit. The first thing I'd like you to recognize is that this is actually a function. All the integrals we've been calculating so far are just numbers. Like when we evaluate the integral, we get like a number. We integrate from 3 to 5, and we get output a number. But keep in mind that this is not a number. It's actually a function of x. You see what it does? So from some fixed a value, where a is a constant, right? We're adding up the area underneath this curve with respect to positive and negative area. Obviously, we've kind of had that discussion. From a to some unknown x value of your choice, if you're coming to me with an x value, and then I give you back like an area under the curve, or at least whatever the definite integral is, from a to your value. So do you see how this is in fact a function of x? And can you maybe see why an accumulation function is a good name for this thing? Because it's kind of giving you the accumulation under the curve up to that point that you've decided. By the way, there's no restriction on x being less than or greater than a, right? If x is greater than a, then you're integrating from left to right. If x happens to be less than a, that's no problem either. We also now know what it means to go from a to x, where x is less than a, right? It's just us integrating kind of backwards. So it's a completely meaningful, well-defined function. So again, a is some constant, and we're integrating from a to x. So let's try this with a little real kind of physics example here. I've got some function. It doesn't have to be, I guess. You wouldn't have to lay any meaning on top of any of these words if you didn't like, but a of t maybe makes me think of an acceleration function, though. So go ahead and start filling in this table. I'll do one of them for you. You're welcome. You're welcome. Yeah, we're starting at 1. By the way, this might not be your favorite thing, but it is kind of the standard notation. Capital F is the accumulation function for little f. Okay. It's not a typo. So do you even get how you're getting each one of these? So like for this first one, what are you doing for if t happens to be 2, what are you doing here? You're computing the integral from 1 to 2 a of s ds. Now, are you okay with the fact that I'm like switching variables up on you? I hope you see why. S is kind of like a local variable. It's kind of a dummy variable is often how what we call it. Because it's kind of, by the time we're done with the accumulation, its role is kind of up. It's kind of like the k in our summation notation, right? It's just there to help you keep track of the sum. But once you're done, it's done. So keep in mind up here, for example, this is a function not of t, but of x. Yes? Same thing here. This is a function of t. This is not a function of s. That's a dummy variable. It would be a mistake to have t's and t's here and here. That would be confusing at best. So, yeah, so this is just a constant, isn't it? 9.8, this is very easy to integrate under. We love integrating under horizontal lines. So, what's this one? And this one, now we gotta, yeah, whatever 19.8 is times 2. What'd you say? And we could even, I guess we could think even about the units on those. And then, yeah, we've just got a rectangle now of width 3 and height 9.8. So what's that? 29.4. I'll trust you. And what's this guy down here? Oh, we forgot that one. Good. Negative 9.8 here. And I think we could go in either direction as far as we'd like with that. And in fact, I think you could maybe even establish a rule for f of t, if you like. Do I have it up here? I didn't actually write it down yet. F of t is equal to, feels quite linear, doesn't it? 9.8 times t. And then minus 1, where how, yeah, like inside some parentheses maybe. You could also do 9.8t minus 9.8, that would be fine too. But actually, I kind of like it this way. Kind of helps you see that when you plug in 1, you get 0. So I actually kind of like keeping it that way. So write it any correct way you like. Okay, so that's cool. I think we did what was asked. We just came up with our very first, we used our first accumulation function, and we were even able, for this case, to write it as an actual function, like an area finding function. It's pretty cool. I hope you'd agree. Yeah? That's a function that no matter where we are, it's not a very complicated a of t that we used to start with, but this new function, big F of t, does in fact give us the area regardless of the point where you ask for it. That's cool. And of course, that function is just the velocity function. Right? Why? Well, because we've already discussed multiple times that the area under the acceleration curve gives you velocity. Or maybe we didn't do it in that context. The area under the velocity curve gives you distance or something like that, right? Do the units work out too? Is the area underneath an acceleration curve? Keep in mind the units on the x-axis, or the t-axis, are maybe measured in seconds. And the function itself is measured in meters per second squared. So what do the units come out to be? Just meters per second, which also confirms that what we think is the velocity function. It seems like it should be a velocity function from the units too. Good. Let's plot it too, just for fun. I have the values you just, here are the acceleration values. It's not very interesting. Here's the velocity values that you calculated a second ago. And I have these plotted here. There's a of t. Here's v of t. Keep in mind that actually you could ask for values halfway in between those points too. So I think these both do deserve nice continuous smooth curves here. So I think that this is the result we have in general, that v of t equals the integral from 1 to t of a of s ds, right? This is a very interesting relationship.
No, I'm not.
Yeah, I mean, I think everyone is starting to see what's afoot here, because you have another relationship in your life, don't you? What's the other? Yeah, v is also called, how else have we related v to a? Yeah, a is the derivative of v. I mean, that is to say, if you went from the function we had a second ago, where was it here? If I had said, hey, this is a velocity function, v of t, and I asked you for the acceleration function, in this particular context, we're still working with very, very basic functions, but still, if this is the velocity function, I asked for the acceleration function, we asked the reverse question, I think you would have been able to say, oh, yeah, it's just a line, it's 9.8 is the acceleration function, right? So we've asked this question before, we've thought about these two functions many, many times, It's just usually we presented this one first and asked about that one, but now we can ask the reverse question, and these two ideas maybe are more connected than we first thought when we were like calculating the area inside of our hands or something, right? Maybe these things are related. So this is the observation that a couple of you just made too. We also have this is true. So together, taken together, it seems that this is what we're saying. It seems like if you integrate under a of t, that's what this says, and then take the derivative of the result, you just recover a of t again. That is, the derivative of the integral seems to just be the original function. Right? I don't think anyone articulated it exactly that way a second ago, but that is one way of saying it, isn't it? Or, if you want, forget velocities and accelerations. Obviously, this gives way, I hope you see, to a much, much bigger and more important idea. That in general, this is true for any function and its like accumulation function. Starting to sink in? There's obviously lots of details, consequences of this thought process to work out, which we'll do in the next months. But this is a central idea in calculus. Are you ready to put it in a box now? I mean, it's already there, but I'm about to put that same result I wrote on the bottom in a box. Because we've stumbled on maybe one of the most important ideas in calculus right here. So there it is. Here's the fundamental theorem of calculus. It does deserve to be painted on the wall. Maybe like out here somewhere, right? There it is. That's above. This gets his room. You can go. I took a picture so you wouldn't have to. The field trip wouldn't have to go any further than the doorway, though. You could just look out and you can see it here. But it's so important that maybe it could be like your first tattoo. It could be this is like the kind of thing you want on like your tombstone, maybe, or something like. I mean, this is. Oh, it's not in a box. I apologize, Kathy. You're right. So stare at it just for a little longer. There are a lot of symbols in that equation, so I like I said, we'll unpack the beauty of this as we move forward. You might be like thinking, I'm really working hard to try and have that be impressive, but it's hard. But I promise it is. Does it make sense to take the derivative of this thing at all? Yes, you should say, because a is a constant, but x is a variable, so it is a function. We already talked about that earlier today. It does, in fact, make sense to be taking the derivative of that thing. And we would be taking the derivative of that thing with respect to x, because it's not just a function in general. It's a function of x, we already talked about. And so that's what we're saying here, right? And then we just talked about the fact that like these kind of, in some ways, undo each other. Thoughts? Comments so far? Do you want to interject? Do you feel the weight of this thing? Vivesh, is that a hand? Who made what? You mean the fundamental theorem of calculus? I mean, there's a story in history, but obviously, like Newton and Leibniz are the ones who we like kind of hold up as having first thought of that, and discovered that that was true. But certainly, even as early as Archimedes was doing things. I don't know that he realized the fundamental theorem of calculus, but he was definitely finding limits of infinite sums. He had the first approximation of pi and things like that, using sums of increasing fineness. But yeah, I think it probably wasn't until Newton and Leibniz and their mentors that this was crystallized. Certainly not in this compact form until Leibniz. I mean, obviously, that's all Leibniz's notation. Is that what your question was? Is who should we give credit to? Who made the painting?
No, you found it.
I think I answered the question, maybe.
Yeah, you answered.
Okay, all right. I don't know if I answered it real well, but all right. Let's play around with this function just a little bit here. Here's a picture of some function, little f. Keep in mind that big F we're calling like the accumulation function, right? So these questions sound just so familiar to us, right? What are the increasing and decreasing intervals for big F? For big F. Now big F is an accumulation function starting at the constant 0. And if we're at like 1, then we get some positive value. What do you think? What's going on? Where does it increase or decrease? Like, can you get a feel for that? Yeah.
I think it's increasing from 0 to infinity.
Yeah. Can you give us a feel for that? Does it?
Well, as you plug in bigger numbers for x, then you just have more area of the graph.
Correct.
I think it's going to be decreasing from negative infinity to 0.
Justify.
If we start with 0 and then we're going to a negative number, so we can just switch x and 0 and make the entire integral negative.
Okay, so yeah, if you integrate from 0 to -1, you get some negative value. Okay, and if you integrate from 0 to -2, you'll get some even bigger negative value.
Right.
So it's decreasing over there? Because it goes from negative to less negative to 0 here. Big F does. I think it's clear in all of our minds that it increases over here. What about over here? I need some more clarification. It's a little harder there. Yeah, Jonathan? No? Rebecca's going to help us.
So it's still like on the positive side of the x-axis, so it's positive area.
I think Josh is right that if you integrate from 0 to -2, you do get a negative result. I think that is true. But that's not necessarily the question. Is it negative or positive? The question is big F increasing or decreasing? Katie?
It is increasing because as you start from infinity and go to 0, the negative area you get becomes smaller and thus approaches 0 to a positive area. So you're getting closer to a positive area, so it is technically increasing.
So you're going to say?
Yeah.
Whoever else out there. Did that compute? I mean, actually start calculating. All it takes is calculate a few values. Calculate -3, plug that in. You'll get, like Katie said, some negative value. Calculate what it would be if you plugged in -2 instead. I think you get a smaller negative value, right? Something closer to 0. Though negative, it is actually going up though, right? Isn't it? It is increasing. And if you plug in -1 for x, you get an even smaller negative value. So it's going uphill until 0. When you plug 0 in, you get 0 for the area. That represents still an increase. And then we talked about over here, of course it's increasing over here. So I think it's increasing the whole time. So did you just feel how your brain just made that happen? You just think about areas? Okay. There's more to the story here, but that's good, that's good. Actually compute, if this really is just x squared, actually compute f of 0, f3, and f of -3. Go ahead and do that. You'll need a calculator maybe for some help. Yes, Nicholas. If little f is constant, if this was a constant, yeah, absolutely. That's what we demonstrated with the a of t equals 9.8 function, right? wasn't V increasing? It was like a line like this. Yeah. If A looks like this, then B looks like this. Yeah. I'll do the first one for you, as usual. Yeah. Right, because that's the integral from 0 to 0. Big F of 3 is the integral from 0 to 3. So someone will tell us what that is in a second here. I guess we'll use T, I guess. And after calculating one of those, you probably don't need to calculate the other. That's 9, you said? Yeah? So what's big F of negative 3? Maybe it's negative 9, yeah. Good, and that goes to show what we were just saying a minute ago, doesn't it? That this, as we go from negative 3 to 0 to 3, if you put those in order, you go from negative 9 to 0 to 9. It does seem that does seem to be confirming what we just set up here. By the way, do we want to just say that this exists only on this interval? I don't know. It's not very well defined in the problem. Negative 3 to 2, 3, 4, 5. This justify your answer part, I'm going to come back to, because I'm not sure that, I mean, we have kind of this like area argument that we just made. We're like thinking, well, I don't know, the area seems to be bigger. So that's one reason maybe, but maybe we can say more about that in a minute. We'll come back to that, okay, I promise, to justify the answer. I don't have anything else to say about B. C? What are the concave up and concave down intervals for big F? Whew. Okay, now this is becoming a headache. How do we read into that? I mean, I can see increasing because of what we talked about. But is it increasing more quickly, or John?
The derivative of the integral function,
Mm-hmm.
we already established that the derivative of the integral function is f of x.
Yeah, I mean, what are we looking at, friends? I mean, we have not yet today, on this problem, invoked the actual fundamental theorem of calculus. What are we looking at? I want someone else besides Jonathan to say it. What is little f? Yeah. Of? Yeah, say it again, just so I can hear it again, Zachary. What is little f?
Is the derivative of big F.
Do you want to say it, Max? Yeah, it's so worth mentioning. I've got it right there. This is so important. This is so critical. This is like the main point of today's lesson, is that we're looking, I don't know if you noticed, we are looking at the derivative of big F. Suddenly this becomes a unit 4 problem, doesn't it? This is just like, hey, we have a function called big F. It just happens to be called big F. But here's a picture of its derivative. You had a question just like this on the test you just took, right? Here's a picture of the derivative, guys. This is a picture of the derivative. So how can we justify when a function increases if we're looking at its derivative? What must its derivative be always if it's increasing? Isn't the function we're looking at here, which is the derivative, isn't it always positive? Except for 0. Point taken. Okay. Because, so now we maybe can fill this in. Why is big F increasing on the interval negative 3 to 5? Well, because big F prime, which equals F, is positive. That is above the x-axis. Yes? That's a good reason. I like that. And we're really, in order to say this, we're using the fundamental theorem of calculus in order to say this. I would definitely, like, if this isn't written on a piece of paper, when it comes to this problem, there will be like a free response question that has this kind of feel on the actual AP calculus test. It's without fail. Write that, like, before you do anything else, right? Like, derivative of big F is little f. Like, you need to have that very clear in our minds, because then all these questions are easy. When is big F concave up or concave down? If we're looking right now, we're looking at f prime. Remember, just use all your first and second derivative test knowledge now. What does it mean for big F to be concave up? Say It means that f prime is doing what? So where is that? 0 to 5, right? So big F is concave up on 0 to 5 because big F, now there are two good explanations here. You could say, because, what would you like to say? Big F, what'd you say? Prime, okay, which is just F, is fill in the blank. Increasing, good, that's one way you could say it. Or you could justify it this way. Big F double prime, which is equal to F little f prime is greater than 0, is positive, right? Those are equivalent statements. I hope you understand that you can justify it either way from the picture, can't you? Is your head doing good things? Okay. And then a similar statement for the interval -3 to 0, right? I guess maybe we should use open intervals here, maybe. Since at 0 it's not either, maybe. We'll be careful. We'll be more careful in the future. Promise. And again, you could say there, big F double prime, which is just F prime, is decreasing, or is negative. What's the instantaneous rate of change of big F with respect to x at x equals 2? What is it? Why?
Because the derivative of big F is the left, and the left is...
Yeah, that's unfortunate. Why did we pick x equals 2? Because if you plug, big F prime of 2 is just little f of 2, which is 4. Yeah? So someone could ask you a lot of interesting questions about these. You know, they could ask about, come up with an equation of the tangent line to the curve of big F at a certain point. You could find rates of change. You could find all sorts of interesting things. This is just the beginning. I apologize for this worksheet. Huh? So yeah, that's the problem with general calculus is that big F prime, the derivative of this thing.
You can also see the same worksheet.
What's that?
So like big F is F prime, a little F prime, right? Wait, no.
No, I think we have to write it. Yeah. I apologize for this. Yes, a 5 worksheet. You'll see what I mean. And you'll realize an apology. Can you even read what you're supposed to do after all these annotations? All right, not much in the way of homework, but there it is. Huh? Oh, she does. Yeah. She knows. I'll get around to updating this soon, I'm sure.
I'm a little insane.